sure we get our notes out. I will record this for prosperity in case anybody needs it later on at some point. Okay, so here we go. Let's talk about quadratic functions. Now we're going to get into the nitty-gritty, some characterizations, some properties. We're going to look at transformations to the parent quadratic function, and we're going to look at different forms in which we can write these quadratic equations. Up until this point, we've solved them using completing the square, factoring, the square root property, but now we're going to get into the nitty-gritty and start looking at the graphs and their properties. So a function that can be written in the form f of x equals ax squared plus bx plus c, where a, b, and c, just the coefficient of x squared, the coefficient of x to the first, and technically the coefficient of x to the 0, the constant, are just real numbers. And needless to say, the leading coefficient a cannot equal 0, or then we no longer have a squared term, and it's no longer quadratic. So if we have a function that can be represented in the form f of x equals ax squared plus bx plus c, then this is in fact a quadratic function. And again, we notice that it is quadratic because the highest exponent of x is 2. It is a quadratic function, but more importantly, represented in standard form, because we're going to talk about two different forms of writing the equation. Now, the graph of any quadratic function is a parabola. And that parabola, that little U-shaped curve, can either open up or down. Depending how it's oriented, the vertex of a parabola is that highest or lowest point. So if you notice that a parabola opens up, so in this case we have the parabola opening up, that occurs when the leading coefficient a is positive. So if a in the standard form of the quadratic equation is positive, the parabola is open up, and therefore the vertex is a minimum point. Okay? If we have a parabola that is oriented downward, the parabola opens down, we would recognize that in the standard form of the equation because the leading coefficient is negative. So if a is negative, the parabola opens downward, and as a result, that vertex is the maximum point. Now, what you will notice is that there is an axis of symmetry, a line, so to speak. It's not really part of the parabola, and I should do this. But you notice that the axis of symmetry is the line that we can fold the graph of a parabola along and get mirror images. Axis of symmetry, line of symmetry. You should also notice that this axis of symmetry passes through the vertex. So this axis of symmetry is not part of the graph, but it's a component, and it passes through the vertex. So how can I write this axis of symmetry? Well, if I know the value of the point, the values that comprise the vertex, I can write the axis as just x equal the x value of the vertex. Now, that's great. We've talked about how to write the standard form of a quadratic equation. There is another form in which we can write a quadratic function. A quadratic function can also be represented in the form f of x equals a times x minus h, quantity squared, plus k. And this is called the vertex form of the equation. Now, a lot of people like to see it represented in this form because it's easy to identify the vertex. The vertex is just the h and the k value. So if I have the equation represented in vertex form, I can just identify the H value, identify the K value, and I have my vertex. If I have my vertex, I also have the axis of symmetry. Okay, so it's not that you can't find the vertex from the standard form, it's just it's easier to identify this, as well as, hint, 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 a little foreshadowing, the transformations that have been applied to the parent quadratic equation. So let's look at the parent quadratic equation. We've talked about other parents and we've talked about transformations that are made to parents, but this is the parent quadratic function. Parent quadratic equation. It's a stripped down version of a quadratic equation. Now, I could, eventually you'll be able to graph this and write tables and talk a lot about it, identify all these characterizations of the parent quadratic function. But right now, if I wanted to graph it, I could easily graph it by creating a table of values. I could choose some X values. Eventually, you're going to want to make sure you're choosing X values that are to the left and to the right of the vertex once you've identified the vertex. But at this point, if I ask you to evaluate this function for each of these input values, you could identify the output values and then have ordered pairs that you could plot and graph this. So let's say we take these values of X and we substitute it into the function. So in other words, I'm evaluating the function at X equal -2. So that's -2 squared, which is what?
4.
4. Okay, so that would give me the point -2, 4. I could do the same thing by substituting -1 in for X, 0 in for X, 1 in for X, and 2 in for X. And if I did that, what would the corresponding outputs be? For X equal -1, we would get as the output
1.
Okay, giving me this point. For the input 0, the output would be
0.
Yes, giving me this point. Input 1, output would be
1.
Giving me this ordered pair. And last but not least, if I let X equal 2, the output is
4.
4. Okay, so then I could plot these points. So I could say -2, 4, -1, 1, 0, 0, 1, 1. We see the symmetry. So I could do a quick little sketch of this parabola, and I can identify some characterizations. So this opens up. That makes sense because our leading coefficient is 1. It's positive, so we know it's oriented upward. But can you identify the vertex? What is the vertex?
0, 0.
And you always write it as an ordered pair. It is a point. It is the lowest point on a parabola opening up or the highest point on a parabola oriented downward. And we will see that that is just the value HK. Now that axis of symmetry, we know passes through the vertex. So what would be the equation for the axis of symmetry?
X equals 0.
X equals 0. Absolutely correct. That's X equal H, and we see the H value is 0. You always write the axis of symmetry as a line. It is the line of symmetry. I do a dotted line, a dashed line, because it's not technically part of the graph, but it's a property, characterization property. Now, what is the domain of this graph and every quadratic function? The domain as an interval.
-infinity to +infinity.
Beautiful. It is in fact all real numbers. The domain for every quadratic function is all real numbers. That will never change because it goes on forever and ever and ever. From -infinity to +infinity, any x is valid. Now, the range will change. So depending on the transformation applied to the parent function. So what is the range of this parent quadratic function in interval form?
Bracket 0 and then infinity parentheses.
Beautiful. And if I asked you, let's just say on a test, to represent it, I may say as an interval, I may say as an inequality. What would be the inequality that represents this range?
Y is greater than or equal to 0.
Beautiful, absolutely correct. And again, as the graph changes, our range may change. The domain will not. And what is the y-intercept of this parent quadratic function?
Just 0 or 0, 0.
0, 0. And again, make sure you always represent the y-intercept as a point because it is the point where the graph passes through the y-axis. So we're looking for when x equals 0. So these are just little aside notes. You wouldn't necessarily write this. This is just for you, unless I ask for it. Okay? All right. Now, let's look at another example. Here we have another quadratic equation in standard form. Could you, for kicks, tell me the way it's oriented? Look at the leading coefficient.
Up,
It's oriented upward, and these are things that you should really think about. Since A is positive, A equals 1, which is greater than 0, it opens up, and those are kind of checks that you should keep track of when you're asked to graph them, so that at the end of the problem, once you graph it, you can go back to the original equation and say, do I even have it oriented correctly? Okay, now again, I could choose X values. You are going to notice as we do more of these, we're going to find the vertex and then you are going to have to determine the X values to the left and to the right so that we actually see the U shape graph on either side of the vertex. So if I substitute in 0, for X, and then 1 for X, and then 2 for X into this equation, let's go ahead and determine what the outputs would be. So substitute in each of these values in and tell me what the corresponding outputs are. For X equals 0, what do I have as the output? 3. Giving me this point. What about if I substitute in 1? What is the output?
0.
Okay. I have another ordered pair on the graph of the parabola. Then substitute in 2, and what's the output?
-1.
Excellent. And then substitute in 3. And what do I get?
Zero again.
Beautiful. And we see the symmetry based on the values that we chose to substitute in for X. And for 4, what in our heart of hearts we should know already what the output is.
It should be 3.
Yes. Okay. So then I could graph this. So I have 0, 3, 1, 0, 2, -1, 3, 0, 4, 3. And I have the graph. And of course, labeling the axes so I don't lose any credit. That's a good habit to get in. All right. What is the vertex of this parabola?
Two, -1.
Excellent. It is the point 2, -1. And again, we always write it as an ordered pair because it's the point of the max or the min, depending on the orientation. What about the axis of symmetry?
X equal 2.
X equals 2. That is absolutely correct. Axis of symmetry. And again, we would want to label all of these things on the graph with the dotted line, right? Or dash, because it's not really part of the graph, but we need to be aware of it. And again, that's x equal h. I see the h value. What about the domain of this and every quadratic function graph?
Open parentheses, negative infinity to positive infinity.
Exactly.
Close parentheses.
It's always all real numbers. And what about the range of this function?
Bracket -1, comma, infinity, close parentheses.
Beautiful. And as an inequality, how would we represent that range?
Y is greater than or equal to -1.
Beautiful. And last but not least, what is the y-intercept?
1, 0, and then is that 3, 0?
No, y-intercept.
Oh, y-intercept, that's my bad. 0, 2.
Beautiful. And again, it is a, not 0, 2, 0, 3, right?
Yeah, I can't read.
That's okay. 0, 3. Again, you always represent it as a point. Now, you went ahead and mentioned something else, so we might as well write them because we're eventually going to have to. What are the x-intercepts? I'm looking at the graph.
1 and 3.
And their points.
1, 0, 3, 0.
Beautiful. And these are exactly the solutions to this quadratic equation. These are the x values. 1 and 3 are the x values so that our output is 0. So these are your solutions, your roots as well. Okay? Now, for kicks, since we did talk about the vertex form of a quadratic function, let's go ahead and look at the vertex form. Okay, now you wouldn't necessarily be able to identify A immediately off the bat, but given what we know, do we know any pieces of this equation?
We know the A and the H and the K.
Okay, and what are they? A is
1.
1, excellent. H is
2.
2.
And K is
-1.
-1.
So guess what? We have the vertex form. We have it. So I can rewrite this as y equals x minus 2 quantity squared minus 1. And if I foiled that binomial x minus 2 and subtracted 1 from the constant, I'm going to get back that original quadratic equation in general form. So we are going to be able to go back and forth from the different forms. Okay, what I would like you to do now is a little exploration, because I want to prove to you that originally when we learned about our transformations made to graphs, parent functions, that these transformations can be applied to a variety of family of functions. So what I would like us to do now is I'd like to look at the vertex form of the quadratic equation. And we're going to play with values of A for starters. So we're going to let H equal 0, K equal 0, and adjust A. So let A equal 2, A equal 3, A equal half, and then A equal -1 and -2. Populate the table of values. You should notice some things changing, some things not changing in these tables of values. You are free to graph each of these, all of these different values of A in Desmos, and then talk about what you notice about how A impacts the parent quadratic function, y equals x squared. Then we're going to look at the quadratic equation in vertex form, and this time we're going to let A equal 1 and H equal 0, and we're going to play with different values of K. Populate the tables, graph both of them in Desmos, and maybe draw conclusions on what K does. How does K impact the graph of the parent quadratic function? Then we're going to look at, again, the vertex form. In this case, A equals 1, K equals 0, and we're going to adjust different values of H. Populate the tables, graph them on Desmos, and describe what happens when we change values of H and how that impacts the graph of the parent function. Then you're going to put all of this together and be able to say what happens for different values of A in general, for different values of H, for different values of K. And then, of course, keep in mind that our vertex is always located at HK. So I'd like you to do that now. Populate this, and then we'll discuss the summary. And again, all of this, you really, you should remember this from when we were working with absolute value functions. So you're doing this now. I'm going to go ahead and let you work on this. I don't think you'll necessarily finish this before the end of class. So